ahead. All right, we're live. So thank you all for joining us today. It's a real pleasure to welcome Peter Hirschfeld from the University of Florida, who's going to be giving us his thoughts about this renaissance in the Ruthenates and his ruminations. So I invite you all to unmute yourselves if you have questions, and so we can have a more interactive and lively discussion. Otherwise, if you can leave your questions for the very end, and you can also post them on the chat, and I will read them for you. All right, Peter, thank you so much for joining us today, and please go ahead.
Thanks, Adrian. I'd like to thank Adrian and the other organizers for the opportunity to tell you about some work that we've been doing on the unconventional superconductor strontium ruthenate. It's based on a recent series of papers with collaborators from Copenhagen and Leipzig and St. Andrews, which you can see listed here, I hope. The latest one should appear on the archive in a day or two. Okay, here's the usual technical problem. I cannot, there we go. Sorry. So here they are. A lot of the work I'm going to show you today was done by Astrid Römer, really talented postdoc at University of Copenhagen, who works with Brian Anderson, my long-term collaborator. And some of the work is also done with Ilya Yaraman, Andreas Kreisel, at the end, if I get to it, with my student Shinibali Bhattacharya and Tom Berline. And towards the end, we'll also get into some of the experiments. I've had a lot of fun talking to various experimentalists, Hans-Henning Klaus and Vidya Madhavan, and actually collaborating with Peter Wall, Luke Rhodes, Carolina Marquez, and Seamus Davis. So this is strontium ruthenate. It was discovered in 1994, so this is an old subject. And the question is, why are we interested today in a superconductor which has a critical temperature of 1.5 Kelvin after all these years? And one reason is that it has this structure, the same structure as lanthanum copper oxide, this perovskite structure. And in fact, it was originally synthesized probably by Yoshi Maino, who's trying to make a cuprate analog compound. But there's another motivation, which I wanted to stress to you, and it's really what drives me in my thinking. And that is that strontium ruthenate is, this is a quote here, is an extremely clean material that makes good crystals with a Fermi liquid ground state before it becomes superconducting, has a simple two-dimensional Fermi surface with one d orbital per sheet. And if we really can't figure out what causes the unconventional superconductivity in strontium ruthenate, we should all go home. And this quote comes from Steve Kivelson, whom I talked to about this subject, well, many times at this point, but starting a few years ago. And he impressed this question on me, that we really ought to do a good job, particularly if one is interested, as I am, in eventually developing a quantitative theory of unconventional superconductivity. Okay, so let's go into some of the background. First of all, if you try to put strontium ruthenate together, you're going to be looking at the strontium oxide plane. I'm sorry, the ruthenium oxide plane, I beg your pardon. And there are three d orbitals near the Fermi surface, the dxy, the dyz, and the dxz. And if you just imagine, if I align them on a square lattice this way with oxygen p states in between, what the bands are going to look like, you can pretty much figure out what the Fermi surface is. The xy states are, of course, in the plane, and therefore they hybridize well in a two-dimensional sense, and they give rise to this so-called circular gamma band of xy character. The two other bands, if I were to neglect hybridization altogether, would be pretty much one-dimensional, because you see these YZ states couple vertically and the XZ states couple horizontally. They extend into the Z direction. And so you'd get something that looked like this before you turned on hybridization and spin-orbit coupling. And when you did, you would get something that looks like the black lines here. And in fact, that's exactly what is seen in beautiful Arpeggios experiments, which have been done over the years, starting with Kyle Shen back in the 90s, and now most recently in this beautiful paper by Tamai et al. Was published a couple of years ago. And here's the cover of Physics Today from 2001, showing the 3D picture. You can see that it's a very two-dimensional material. In particular, the gamma band has almost no corrugation, but the XZ-YZ bands have a little bit of corrugation. It's still very two-dimensional. Now, the other reason there's been so much interest in strontium ruthenate over the years is that very early on, it was declared to be an analog, an electronic analog of superfluid helium-3. So this is Morris Rice and Manfred Sigrist, who, on the basis of a number of considerations, proposed that it should probably be a P-wave state, and that it would not only that be a chiral P-wave state, by analogy to the Anderson-Brinkman-Morel phase of superfluid helium-3. And this is a state that spontaneously breaks time reversal symmetry. And this has been seen in a couple of different experiments. So that gave initial confirmation to this proposal. And that comes, for example, from USR, which sees an onset of a time reversal symmetry breaking internal magnetic field at 1.5 Kelvin, which is TC, and the polar Kerr effect from Kapitulnik's group, 2006, a little bit later. So, okay, this was a very nice picture. And I think probably the most direct evidence that people believed in as a proof or strong evidence in favor of this triplet character was the night shift. It was done by a number of groups, starting with Kenji Ishida. And it showed something very unusual, namely that the night shift didn't care about what happened at TC, did not care about the formation of the superconducting condensate. And so that's something you do not expect for a singlet superconductor. When the electrons are bound into singlet pairs, then you need to supply a significant energy to break those pairs. That would be the gap energy. And so you should expect the susceptibility, or the night shift, to be exponentially suppressed in an S-wave superconductor and have a linear temperature dependence in a D-wave superconductor. Can you guys see my cursor? Adrian?
No, unfortunately, we don't see it.
We don't see it.
No.
Oh, okay. Well, I'll just have to allude to things.
I can see it. It's white on the white background, but it's there.
Oh, yes, it is there. It is there. When
Okay.
you move it, we can see it. Yes,
there's a delay,
yes.
I guess. There's a delay. I'll try to move it a lot. Okay.
Yeah.
And so with a P-wave superconductor of this ABM type, you expect to see a totally flat night shift if the field is in the plane, because basically what happens is you have two independent spin pairs, spin up and spin down, and they basically respond to an external magnetic field exactly the way a Fermi gas does, and so you don't the condensation doesn't affect anything. When you put the field in the C direction, this is assuming that the triplet D vector is in the C direction, then you do see a suppression. This is what you should see. In fact, this initial experiment was just done for field in the plane. And so it was quite a striking result at the time and pretty much convinced everybody that this was a triplet superconductor. Of course, there are many reasons to be interested in chiral P-wave superconductors, including quantum computing and so on, but I'm not going to go into that. So just to show you some pictures to classify these various states, when we talk about singlet pairs, in the strontium ruthenate case, we'll be talking about competitions between S-wave, dxy, dx squared minus y squared g. These are classifications in tetragonal symmetry. These are the allowed states. And the px plus ipy state that we're talking about, this chiral p-wave state, is a linear combination of these two states, px and py. It's a two-dimensional representation, which can, in principle, break time reversal symmetry at the transition if it forms in this chiral phase with an internal phase between the kx and ky components. On the other hand, you can also have a time reversal symmetry preserving phase, which is called a helical phase, which are these combinations of kx and ky, where x and y hat are now the spin vectors in the problem. So there are various possibilities, and I haven't mentioned yet non-unitary solutions, which are also in principle possible, although nobody knows how to stabilize them. Okay, now, historically, that was the situation starting, I don't know, a decade or so ago. And the first fly in the ointment, for those of you who don't know that expression, that means a problem, occurred when the susceptibility turned out to be the wrong shape in the other field direction. So I'll remind you that of that picture I showed you, that if you have a triplet superconductor like the A phase of helium-3, then the susceptibility is a tensor quantity. And so you have two eigenvalues which are temperature independent. That's what you see when you put the field in the plane. And you have one which is a Yoshida function, where the temperature dependence gets suppressed very strongly. In helium-3, you pretty much only see the temperature independent part because the D vector can rotate. But we assume that crystal field splitting and spin-orbit coupling pin the D vector to the C axis normally. And therefore, we expect to see both eigenvalues for the different field directions. And that's not seen, okay? You see a temperature independent result for both field directions in 2004, this Murakawa paper. So this contradicts the chiral state prediction. Here's some more flies in the ointment that came up pretty soon thereafter. If you have chiral p-wave state, you expect to see edge states in a single domain sample. Those were looked for by Cam Muller's group with scanning squid microscopy, and they were never seen. There are various explanations for that, but I'm just telling you the simplest, straightforward predictions. And you should see Pauli limiting. Yeah, sorry, you should see no Pauli limiting if it's a triplet superconductor. But here there is some claim of Pauli limiting in this Yonezawa paper. In the thermal conductivity, this is Louis Teifer's group. The claim is that they see evidence for vertical line nodes in the sample. That's also not consistent with px plus ipy, which in the two-dimensional system should be a fully gapped state. And finally, you can look at the magnetic field in the plane and rotate it and look at thermodynamic properties and see oscillations. And those are mostly consistent with this idea of linear line nodes in the vertical direction. Not all of them. Okay, so I claim that this P-wave house of cards started to fall. At least the foundations were eroded significantly a couple of years ago when Stuart Brown at UCLA and his group made a test of the old NMR data by varying the RF power in their night shift experiment. And what you see is that this is the NMR line, function of frequency. What you see is when you lower the amount of RF power you're putting into the sample, which of course enhances your signal, so it's nice to have a lot of RF power, but it can also do something else. It can also heat your sample if you're not careful. And what they saw is when they worked at very low F power, that the signal wasn't as good, but on the other hand, the peak of the NMR line moved to lower frequencies. And that is precisely a representation of a decrease in the night shift as a function of temperature. This is at, let's see, This is 20 millikelvin. All of these curves are at 20 millikelvin, which is way below TC. So they published a paper saying, look, we think the old results from Ishida et al. Were actually due to too much RF power in the sample. So you didn't have control over the temperature. And therefore, we think it's actually a suppression of the night shift inconsistent with the chiral state. And I should mention, this is one of the times in my career when I've been really proud of the condensed matter community, because within a few months, Kenji Ishida himself had produced a paper repeating Stuart Brown's experiment. That doesn't happen very often, that experiments get repeated, and confirmed the result and published a paper saying, I see the same thing. Stuart has another paper recently, which is even more striking in some ways, the results. And that is a comparison of the night shift data with the specific heat data. So imagine a chiral P-wave superconductor. There are two possible contributions to the spin susceptibility. The condensate itself carries spin, and so it can respond to an external magnetic field, a small one. In addition, when you break pairs, there are quasi-particles floating around. They carry spin, and they can also respond. On the other hand, the specific heat only measures quasi-particles. So it's only measuring entropy, which is was not provided by the condensate. So if you plot as a function of field, both the night shift, those are these symbols here in color, and the old data from, let's see, my screen is being covered. Let's see. There's a little thing on my screen that says I'm sharing, and it's covering the name. This Nikishima. I'm sorry, I've forgotten the gentleman's name.
Ishizaki.
Anyway, this is Nishizaki. Thank you. That's embarrassing. From 2000, the paper from 2000. These are his data, and they were plotted on Stuart's scale here. And you can see that they are pretty much consistent with each other. And this paper puts an upper bound on the fraction of triplet pairing of about 10%. So that's the claim. All right, so you've seen the background now. And now I'm a theorist, and I'd like to ask some theoretical questions. And that is, for example, if we restrict ourselves to the notion that a lot of unconventional superconductivity comes from the exchange of magnetic excitations, then what kind of order parameter should we expect in a strontium-ruthenate system coming from spin fluctuations? And we're not the first people to ask this question. Thomas Scafidi and Steve Simon and their collaborators have done a lot of work on this problem. There's a group led by Zhang from a couple of years ago, and Fucheng Zhang also has a paper. And here's a series of papers that Brian Anderson, Astrid Römer, and the people I showed you at the beginning all wrote together. And recently there's a paper from Steve Simon again and his group about a 3D version of this calculation, which is quite interesting. Okay, and I'm sure I'm missing some as well. So the question is, I can't see my own slides. That's not fair. What's the night shift for these various superconducting orders? I think is what it says. And if you make a theory based on spin fluctuation pairing, you're supposed to be describing the effects of spin fluctuations. You better have the spin fluctuation spectrum itself consistent with what's known about the system from neutron scattering. So one other thing we know about strontium ruthenate is that there's a relatively significant, for a d-electron compound, spin-orbit coupling. And this has been studied by a number of Arpeggios groups. Most of the splitting here of the Fermi surface along the 45-degree directions, I hope you can see my swirling cursor, is due to spin-orbit coupling. And you can also see its effect on the susceptibility, the spectrum of spin fluctuations, if you will, explicitly by noticing that the chi-XX fluctuations are different from the chi-ZZ fluctuations. So there's a direct signature of spin fluctuations in these experiments from Marcus Braden and others. So we have spin-orbit coupling. So spin is no longer in principle a good quantum number. And we're also going to have mixing of singlet and triplet components of the pair inevitably. We can deal with the spin-orbit coupling theoretically by writing down a tight binding model. And the L dot S term is the on-site term is placed in these off diagonal in this particular basis, which is convenient for representing spin-orbit coupling in strontium ruthenate. It's been used by a number of authors. And so you can see the differences caused by spin-orbit coupling in the Fermi surface. Here's the density functional theory calculation where there's no hybridization of the XZ, YZ bands, or very, very small. And then this spin-orbit coupling opens up these this difference between the bands, splitting between the bands at the Fermi surface. Okay, so we calculate the spin response given the Fermi surface, given the band structure, I should say, and the random phase approximation, which is what we're going to be using here, and some notion of the interactions, which I'll show you in a second. We can calculate the spin response and compare to experiment. So first of all, to go back to the original motivation for why strontium ruthenate was interesting, the original proposal was that it was a nearly ferromagnetic superconductor. And then you would expect the spin fluctuations to be peaked around Q equals 0, ferromagnetic spin fluctuations. That turns out to be not the case. That's been known for quite a while. In fact, the spin fluctuations are incommensurate and antiferromagnetic. The main peak is this thing we call Q1, which is this peak in the calculated susceptibility. There are some subsidiary peaks. There is a sort of quasi-ferromagnetic peak at relatively low Q. It gives you kind of a ridge in the scattering intensity, in the fluctuation intensity, I should say. And then there's another peak called, I'm sorry, this is gamma over here. This is the wrong direction. Q2 is the one I want to point to. That's the quasi-ferromagnetic peak. And then there's this very, very narrow peak called Q3, which has only been seen in one time of flight experiment. And the philosophy now of the calculations I'm going to show you is to take this model, which has a lot of parameters in it. And you won't believe my answers if I have too many parameters. I'm going to constrain most of them by requiring that the spin susceptibility calculated in the theory in the normal state agree reasonably well with what's measured in experiments by these neutron scatterers. So the theory starts by taking the band structure and including the interaction terms with a multi-orbital system on a given site. So those are the standard Hubbard interaction. If you have the orbital the same, you have a U prime if the orbitals are different, and you have a Hund's coupling term and a pair hopping term. This is the so-called Hubbard-Kanamori Hamiltonian. It's very standard for these multi-orbital correlated systems, and that's what goes into our interaction. You sum in spin fluctuation pairing theory a bunch of ladders, and I'll come to that in a second, I guess. Anyway, these are the terms that go into the bare interaction in the theory. Okay, and some of these interactions are constrained by spin rotation invariance. So there aren't 4 parameters, there are actually only 2. And we're going to pair in both the singlet and triplet channels and compare the results of the gap equation that comes from calculating the effective interaction. Here is the effective interaction for a pair of electrons with arbitrary spins and arbitrary orbital indices, opposite momenta, scattering into 2 new momenta, opposite momenta, and new spins and new orbital degrees of freedom. It depends on the particle hole susceptibility with lots and lots of indices. And basically, this gets plugged into an expression, which many of you will recognize, because it looks structurally just like the one-band expression that you would see in a calculation for the RPA in a one-band Hubbard model. you have the enhancement of the spin susceptibility, 1 minus chi0 over, times u, the Hubbard interaction, times the chi naught. And in principle, there is a charge piece somewhere, which I've left out, I guess. Yeah, well, this is just the part that's enhanced by the spin fluctuations. Okay, so you then transform this expression to to band space. I can't read it again. And then you get an interaction to connect the various states on the Fermi surface, pair scattering. So there are a couple of parameters left, which we play around with a little bit. One of them is essentially the chemical potential, which is used to take the DFT downfolded tight binding parameters and to adjust to get the reasonable Fermi surface. So we allow ourselves to play with that a little bit. And we allow ourselves to play with the spin-orbit coupling amplitude over some range. And so you can see an example of something that agrees reasonably well with experiment in terms of the spin susceptibility, which is shown here. This is chi zz. It's a function of qx and qy at omega equals 0. And you can see the presence of these two peaks. Here's an example of another susceptibility, which just has a large Q2 peak. And this is not, this would be nice if I really wanted to have a chiral P wave, but in fact, this is not what drives, this is not what's seen in experiments on strontium ruthenate. So the phase diagram that we get for the, let's call it the realistic case, it actually involves a number of ground states that are closely competitive. This includes a dx squared minus y squared state. I think this says nodal S prime state down below, and a helical phase. Okay, the chiral state is nowhere to be seen. If you crank up the spin orbit coupling a lot and you work in this regime where Q2 is enhanced, you do see the chiral state eventually, but it's really not favored. Okay, now I'll draw your attention to these white points on the phase diagram. Some of them, these are places where we have evaluated the theory in a little more detail, and some of them are very close to phase boundaries. So that can be important for a reason I'll tell you in a second. Here are the structures of solutions, which I think are evaluated near this point here, this particular point here. And they look rather complicated. Okay, here is a D wave state. This is a dx squared minus y squared state in the sense that this is an eigenstate of the linearized gap equation, which has this particular symmetry. It's this irreducible representation. And it's the leading one in some parts of the phase diagram. Now, what do you expect for x squared minus y squared? You expect a node along the 45-degree direction. There it is, but it's hard to see. Hope you can see my cursor going up in the 45-degree directions. There are 3 bands and therefore 3 gaps plotted with different colors. On the other hand, there are some other directions which also look nodal. And those are these directions here. And those turn out to be accidental nodes in the dx squared minus y squared gap. Okay, they're driven by the fact that there's orbital mixing due to the hybridization of the bands in those regions. And they show up in other gaps as well. Here's something which I call an S-wave state, but it has exactly the same, nearly exactly the same accidental nodes in those positions, again, due to the orbital physics. Now for the triplet states, there's the helical state, which in this particular calculation had no nodes at all, and the chiral state, which had nodes, but in the different directions here. Okay, and so I just want to make the point that we're all, to some extent, in unconventional superconductivity, used to thinking about the competition among various superconducting channels in terms of simple either Fermi surface or Brillouin zone harmonics. But it may be important to remember that there are higher order harmonics which are involved in creating these leading pair states as well. And yeah, I think I'll go on. So to compare with experiment, we calculated the night shift. This is Astrid again. her calculation, and you can see calculations. There are two curves in each plot, one for the field in the plane, one for a field along the z directions. I hope you can see that. I know the legend's a little small. And here's dx squared minus y squared. Here's a linear combination, s prime plus I dx squared minus y squared, helical and chiral. Chiral is flat, as we knew, as a function of temperature, and therefore is ruled out. Helical is potentially consistent with experiment, dx squared minus y squared also, and the time reversal symmetry breaking state in the condensed state below TC, S plus ID, also consistent from this point of view only. Okay, so yeah, so we've been working close to this point where S and D are nearly degenerate, and so this gives rise to a new possibility. What if the time reversal symmetry breaking came not from a two-dimensional irreducible representation like the EU representation, which is the chiral P wave, but instead from a linear combination of two singlet one-dimensional representations. Now, from the point of view of elegance, that's somehow less desirable, but there's some evidence that it might actually be the case. Here is an experiment from Hans-Henning Claus's group showing that there's a muon experiment showing that the superconducting TC, which is this curve here, doesn't quite meet always, for some samples at least, the curve where the muons see the onset of a time reversal symmetry breaking signal. So if this were a chiral P wave, a two-dimensional representation, those would have to be the same temperatures, but they're not exactly. And also for later work, I'll point out that this is a plot with strain. The strain increases the distinction between the TC and the time reversal symmetry breaking temperature. So what are the possibilities here? Well, the S plus ID, which I mentioned before, it breaks time reversal symmetry because it's a complex state. It's not chiral, so it won't explain the Kerr effect intrinsically, but disorder, we know, also induces a Kerr effect. And it's hard to tell what the magnitude should be, so that might actually still work. And it's two irreducible representations, so we would get that the time reversal symmetry breaking is less than TC. The helical state doesn't work by itself, but you might get a time reversal symmetry breaking combination in the same way, S plus, but this is not possible for the helical states I've showed you so far because there are no nodes. And finally, a state that has been mentioned in the literature, in particular by the NMR group that made the original observation of the suppression at TC, this Kz times Kx plus IKY state, the E1G state. This is intrinsically a three-dimensional state. You see the fact that there is an involvement of Kz, which means there's a node in the gap at Kz equals 0. And it means you're pairing electrons in two different planes. So that means in the calculations that we've done so far, you cannot actually address this state. So it's an open question. It was addressed, however, in a calculation by Steve Simon's group. And they did not find this state, did not find that this state was favorable. Okay. So it is still, I would say, to the extent that we don't necessarily trust spin fluctuation theory calculations implicitly all the time, is still in the running as a candidate, but maybe a dark horse candidate for the ground state here, as far as we're concerned. Okay, now I showed you the effect of strain before. Let me come back to that. This is a very interesting effect. This story was started by Cliff Hicks and Andy McKenzie when they measured the effect of strain on strontium ruthenate, a little bit of tensile strain and some compressive strain, and you see that it had a big effect on TC. And also that the effect on TC was not linear, strangely enough. It was actually quadratic or close to quadratic. And this big peak occurred at some particular value of strain where the Fermi surface has been distorted. And actually, it's been pretty convincingly proven so far. I'm not going to show you the experiments, that what happens is the Van Hove point actually gets close to the Fermi surface. when you're at this particular value of the strain, and therefore you expect TC to go up because the density of states is enhanced. And the MUSR guys, this is Hansen and Klaus again, gave this phase diagram. They went a little bit further, and they showed eventually you get actually to a magnetic phase. So there's the creation of an SDW phase beyond the superconductivity, and the splitting of TC and the time reversal symmetry breaking critical temperature that I mentioned before. Okay, so we looked at this a little bit as well by simply including the strain in a model of the hoppings. You change the X hoppings a little bit differently than the Y hopping that are shown here, and we try to keep the Poisson ratio consistent with experiment while we do that. And then you can look at the same calculation again, showing the competition between the various pairing channels as a function of strain. And what happens is this S-wave state is enhanced in this particular case, and the others are suppressed. This doesn't happen for weak coupling. That happens only at intermediate coupling. So this quote unquote qualitative agreement with experiment, the fact that the critical temperature should be going up while the time reversal symmetry breaking temperature, which is only possible when you have two irreducible representations, has to be going down. So that's a nice result. And in addition, the same calculation showed indeed the stability of an SDW phase. Within the RPA theory, this corresponds to hitting the Stoner criterion at around a strain of about 15%. So that's all nice. Here's the fly in our ointment. The experiment by Brad Ramshaw's group came out a little bit later. This is just last year, showing that the sound velocity and the elastic constants that you deduce from the sound velocity in the superconducting state, across the superconducting transition, I should say, behave in a very characteristic way, which is telling you something about the symmetry of the superconducting order at the transition. In particular, there is a discontinuity, that's what they call it in their paper, in the C66 channel or B2G channel. And this has important implications for the order parameter. So there's a big table, and there's a very nice discussion in this paper, which I don't have time to go through, but I would say that the conclusion is that the product of the two components of the order parameter have to together transform as XY in order to explain this experiment. So if you want to believe this one particularly, and I think it's a very strong symmetry-based experiment, then the state that we proposed in this earlier calculation, D plus IS prime, or IS plus ID prime, doesn't matter, is not consistent with these elastic constants. Okay, so that got shut down. Now, shortly thereafter, there's a proposal from Steve Kivelson and collaborators, Sri Raghu, Ronnie Tamale. They said, okay, phenomenologically, it's pretty easy to explain a lot of data on strontium ruthenate by taking dx squared minus y squared and combining it with another singlet representation that I showed you before, the G representation. Usually we don't get as high as G in these discussions, but this time we will, okay? And it's a function that has the form xy times x squared minus y squared. It has that symmetry. It's time reversal symmetry breaking. It's not chiral, so it would have no edge currents, consistent with the molar experiment. It's consistent with ultrasound results. It has nodes because D x squared minus y squared and G share symmetry-driven nodes. It has two components, and it has a sharp drop in the night shift at TC. Furthermore, it was, in a certain sense, they tried to define as natural, a good candidate. And they compared with an experiment, with a theory which had been done looking at the pairing ground state in a single band Hubbard model of the various states when you introduced a nearest neighbor Coulomb interaction. Everything I showed you before was on-site interactions only. And now we're going to say, okay, well, there really should be a Coulomb between two electrons sitting at site I and site J if I and J are nearest neighbors. And one thing that happens when you turn up the nearest neighbor Coulomb interaction and get close to half filling is that you stabilize this G wave state. And it's right next to this D wave state, so there should be a point here playing the same game that allows for this kind of a combination, which should be energetically favored. So is it natural? So Ostrand set out to actually decide for the strontium-ruthenate case, is this really going to be a natural candidate for pairing? And it's quite involved, and I think it's really a tour de force calculation that she did, a multi-orbital nearest neighbor spin fluctuation pairing calculation, but she did it. And what goes into it is a generalized interaction, which has the on-site terms and the nearest neighbor terms. And you sum, again, following the philosophy of Burke and Schrieffer, all of the bubble diagrams, and I drew some out here just to show you how many indices there are, and all the ladder diagrams, which I didn't draw, and also a couple of diagrams which show up in this expression, which you don't expect necessarily. And they show up also in the multi-orbital Hubbard model. They're vertex corrections, but they're included in this. We don't think they play a super important role, but I'm just going to mention that they're there. Okay, so that's the calculation, and here's the result. We do find that the G wave is favored by nearest neighbor interactions. But on the other hand, almost all of the other ones are as well. And relatively speaking, what the winner in this game are the D wave, but the dxy component now, and the S prime state again. I could tell you in detail why xy becomes favorable, I think, but in any case, I'm going to bypass that for now. This is a state which has very deep gap minima, nearly nodes, because the gap minima of the xy and the S prime coincide just as before, these accidental nodes. So it's consistent with all the experiments telling us that we have nodes. It is complex. It has two components. It is also consistent now with the ultrasound. So we're proposing that maybe this is a good candidate for pairing in the strontium-ruthenate system, S plus IDXY. Okay, and I want to make sure that you understand, if any of you read a paper by Hae-Young Kee's group, that this is distinct from the S plus IDXY orbital interband triplet state that they proposed. This is a predominantly singlet state. I don't think I have time. Yeah, I don't have time to show you the night shift, but it's consistent with the experiments as well. Okay, so I want to at least start end maybe with this question and a couple of remarks. I've shown you a lot of calculations. There are a lot of parameters. You're probably saying to yourself, well, that's kind of nice, but why should we really believe this? And it would be much nicer if we could constrain the calculations as we have in cuprates and other unconventional superconductors by knowing something about the structure of the gap itself. The problem is that a 1.5 Kelvin superconductor, it's hard to use the natural experimental probe, namely angle resolved photo emission, to determine that gap. And there are other experiments like magnetothermal oscillations, which so far are inconclusive. As I mentioned before, Josephson tunneling effects seem to depend on domain distributions. I would say they're inconclusive. Dale Van Harlingen might disagree with me. And then the one I want to push a little bit is quasi-particle interference in STM experiments. Remind you briefly that what this measures is the wavelength of the Friedel oscillations in the system when you have some disorder. They're sensitive to a single domain. In principle, they're sensitive to the sign of the order parameter. And the STM probe itself, of course, is very high energy resolution at low temperatures. The quoted energy resolutions are of order 10 micro EV. So that's capable of resolving the superconducting gap for sure. There are 4 papers on STM and strontium ruthenate. There's Fermo et al., Wang et al., Marquez et al., and Sharma et al. I'm going to show you each one of them a little bit. So this is the Fermo et al. This is from Seamus Davis's group. And what they measured is a nice V-shaped gap in the spectrum. These are various temperatures going up to TC. So it's a normal gap closing at TC and a V-shaped gap, which might say line nodes, maybe D wave. And one thing I want to point out, because I'll come back to it, is that the value of the zero bias density of states is actually not zero, as you would expect, but something pretty large, maybe half the normal state value. You might think, oh, then maybe this is something exotic like a non-unitary state, Bogoliubov Fermi surface. But in fact, if you look at the specific heat, there's no evidence at all that there's any zero temperature density of states. So this is probably an imperfect coupling of the superconductivity to the surface. Again, I'll come back to that. Fermo et al. Point that there's only one gap scale visible, no sign of any multi-gap structure. They argued that what's happening in this experiment is that they're tunneling into the 1D bands, the XZ, YZ states. And the XZ states, because they're the orbitals, if you think of them as an atomic orbital, are located in the plane, they don't couple very well to the STM tip. Here's a paper from Vidya Madhavan's group where they looked at QPI, and they saw something strange, which is that low energies, this looks like a superconducting gap, but it isn't. If you look carefully, you see this is 5 MeV, way bigger than twice TC. And it's not centered at zero energy either. So this is a little pseudo gap that forms, which you do not get from any of the density functional theory or related calculations. And so this group said, okay, what's happening is there's some surface reconstruction, and we can see the wave vectors associated with this reconstruction in our QPI patterns. QPI, here's the theory, okay, and here's the experiment, can be reproduced by that assumption, not all. Here's the next paper from my collaborators, Peter Wahl and his postdoc Luke Rose and his student Carolina Marquez. And they investigated this reconstruction in a little more detail. They said what's happening here is a rotation of the strontium ruthenate, the ruthenium oxide octahedra, so as to produce inequivalent oxygen sites. Now, that doesn't necessarily produce by itself inequivalent strontium and ruthenium sites. But nevertheless, that's what they saw in STM. They saw close to the Fermi level inside this little pseudogap region, they saw these checkerboard patterns. And so there is some kind of order on the surface, which is probably not reflecting anything in the bulk. And they related this to the Van Hope singularities. I'll come back to that. Some of these XY features are visible and some are not. So what's going on there? So we did a calculation, and I am now stuck. We did a calculation, there we go. To understand the role of the XY states, which involves invoking the actual Wannier functions that are used, that enter the tight binding models that are used. So Tom Berline here does a calculation for the strontium ruthenate surface and produces a set of Wannier functions, which are characteristic, centered on the ruthenium atoms, but which include the effects of the nearby oxygen and strontium states. And Andreas Kreisel has done this calculation to, first of all, check this assertion that the XY states are not involved in the tunneling process. Well, if you look at the extent of the XY magnitude now, off into the distance, many angstroms away from the strontium ruthenate surface, you see that indeed there is a factor of 5 or so smaller amplitude squared for the wave function in the XY states. On the other hand, that's not the major effect near the Van Hove energy. I'll come back to that in a second. Sorry, these are pictures of these Wannier functions, cuts through the plane above the surface, and you can see what happens in the bulk band structure. XY state certainly has the symmetry of an XY atomic orbital, XZ, YZ the same. And what happens when you rotate these octahedra, as believed to take place in the surface reconstruction, is that these XY orbitals get strongly reconstructed, and in fact mix in little pieces of Z squared orbitals, and therefore couple a lot better to the tip. So we can fix the amplitude. We want to understand the pseudo gap. I'm almost done here. We want to understand the existence of this little pseudo gap. That's due to some additional order, which we haven't discussed so far. And so very similar to this Marquez paper, in this new paper, we are assuming some pneumatic order on the surface of two different types along the X and Y bonds and along the 45-degree directions. Blue is positive shift in the hopping, red is negative shift in the hopping. Put this into the Hamiltonian and then tune the amplitudes of those orders to get the shape of the pseudo gap that's observed in experiment. And this is basically the 4 Van Hove peaks that show up in this kind of a calculation. One of them is pretty dramatically suppressed. This is the continuum density of states obtained by now taking the Wannier functions and weighting the lattice Green's function that you calculate in theory. This allows you to actually calculate the density of states a few angstroms above the surface of strontium ruthenate, rather than just one piece of information per ruthenium. Now, I'm going to point out that there's absolutely nothing happening in this blue region of energies, which is roughly speaking where the superconductivity ought to be happening. I'll come back to that at the end as well. There are a lot of consequences of this pneumatic order that we assume that we're now able to predict and compare with experiment based on this one assumption, which came from tuning the parameters for the pseudo gap. There are chiral impurity states. There's the existence of this checkerboard pattern, which comes out qualitatively, but not quite quantitatively. We think because the Wannier functions are not treated accurately at long distances. And then there's the QPI patterns, which has these features which are attributed to the XY states, which were ignored before and which we now can explain. This is all done by taking the density of states calculated in theory from the continuum Green's function and calculating a so-called topographic conductance map, which is obtained at a position Z of X and Y, where Z of X and Y is done by solving this equation with the set point current and the set point voltage for Z itself, and then plugging it in here. Okay, so I am going to skip. Well, I'll just, I'm sorry. Can I have one more minute, Adrian?
Sure, please. Be my guest.
Okay, thank you.
Absolutely.
Thank you. You guys have been very polite and not interrupted me at all, but I'm still over time. So I'll just say that the last SCM experiment I wanted to mention is from the Davis-Madhavan group, joint effort, and they also did QPI. They did QPI now in the superconducting state, and they claim that the results are consistent with D-wave state, ordinary X squared minus Y squared state. Again, they ignore the XY orbitals, and they find some peaks in their QPI pattern, which disperse a little bit, and they say that these are consistent with what you'd expect from the X squared minus Y squared living on these 1D bands. Okay, there's obviously a lot of structure in these QPI patterns, which is not represented by these little circles, which are the expected scattering wave vectors. And so I think that there's some open questions. And I will mention to close, sort of begin the closing of the talk, that to me, this is a little bit of a mystery, because if you talk to the authors of this paper, they will tell you that the data that they obtained and they published in this proceedings of the National Academy paper were obtained within the first few weeks of running the experiment. And they tried for a year and a half after this to get data again, and they never found superconductivity at all. So there is something mysterious about the surface of strontium ruthenate. There is this reconstruction going on. Often, to get rid of the reconstruction, people disorder the surface in order to get the bulk bands. Arpeggios does this routinely, as I learned. Okay, so the question is, why, if you have the cleanest possible strontium ruthenate, the best surface, and it has, I assume that's the one that has this reconstruction, why do you not see the superconducting gap? Okay, so is it a tip effect, which I think Peter Wall believes in his experiment, or is it some actual differences between the surfaces which are not coupling well to the bulk, depending on whether they're reconstructed or not? I'm just putting this out as an open question. Okay, I'm going to skip our calculations and just show you my conclusions. There's the renaissance, which comes from these recent NMR experiments. The idea maybe to go back to the old notion that we can get a two-component state and a time reversal symmetry breaking state that are consistent with the new experiments by combining two nearly degenerate irreducible representations. Our favorite at the moment is S plus I dxy. The way to get direct measurements of the gap, I guess the best chance we have is STM and quasi-particle interference. There's the mystery I just mentioned. Why is it so difficult to see superconductivity on the clean surface? And I will close by saying that I think the convergence of theory and experiment looks possible within this renaissance, now that the NMR is understood, but there's a lot of work to be done. So there's no need to go home yet. Okay, thank you very much.
Thank you, Peter, for a very nice talk and a very nice overview of theory and experiment. Now the session is open for questions. So please raise your hand or feel free to unmute yourself. Any questions from the audience?
Uh-oh.
Then Peter, good to see you.
There we go. Hi, Yoichi. Hi.
Hi. One of your possible candidate state was S plus IP, right?
Yes.
But
that's a state. Yeah, go ahead.
Yeah, that's inconsistent with the inversion symmetry. So how can you conceive that? Triplet and singlet characteristics in the inversion symmetric system.
Let's see. I'm allowed to mix singlet and triplet because I have spin-orbit coupling.
Well, even in the presence of the spin-orbit coupling, I think maybe it depends on the form of the spin-orbit coupling. Yeah. Okay.
I think you're correct that I have to have well-defined states of well-defined parity at TC.
Correct.
Okay.
Yeah.
But I can have I can always have even parity states and odd parity states, which are close, accidentally close in coupling, in dimensionless coupling. Okay, because of the band structure. And then if I insist that they be exactly degenerate, then in principle, when I go down into the condensed state, I can gain condensation energy by combining them. So each one is individually a parity eigenstate, you're correct. But the overall one breaks inversion symmetry.
Okay, so overall parity is always a good quantum number. Is that correct?
It's always a good quantum number at TC. But you can break any of these symmetries in the superconducting state if you want. You have to explain why it's energetically favorable. There's a paper by Thomas Scafidi who makes some arguments that if you start close to the one-dimensional picture, the 1D band picture, and do a perturbation analysis, that it might be natural in some sense to get this combination. But it doesn't come out of what we've done so far.
I see, yeah. And I have one comment. So there is another triplet superconductor, which is copper doped bismuth selenide. And on this system, the STM always fails to see robust superconductivity on the surface. So, and the bulk is surely superconducting. So this failure of the coupling of the STM tip to the bulk superconductivity exists not only in strontium ruthenate, but also in copper bismuth selenide. And this is really mysterious.
Thank you very much. I didn't know that. Yeah, it's a problem that hasn't been investigated very much, and I think one has to think about more deeply.
Yeah, thank you very much.
Any other questions? No more questions?
Okay, I guess everybody's tired.
Or I guess you were very clear. There's one question here on the chat.
I'm never that clear.
Yeah, from Nick Poniatowski. Does a chiral state require that both order parameter components belong to the same reducible representation?
Yes, the chiral states that we've just been discussing are always 2D representations. Oh, I'm sorry. No, you can have a chiral state. Maybe I misinterpreted the question. You can have a chiral state, which is a linear combination of two 1D representations. The best example is d plus id, where you have d plus I dxy, sorry, dx squared minus y squared plus I dxy. That's a chiral state. But the chiral states I was discussing were p plus ip. So they belong to the EU representation. That's two-dimensional.
All right. Thank you. Any other questions? All right. If not, I guess let's thank Peter one more time for a beautiful talk, and thank you all for joining us today. And have a wonderful rest of the week, and we meet again next week. I remind you that the week of the March meeting, we're not having a seminar, and we'll resume the week after. All right. Goodbye, everyone.
Thanks, everyone.